So in this demonstration, we will be simulating the flow over a flapping NACA-0012 airfoil. The NACA-0012 is a symmetrical airfoil, and we will be simulating the flow when the airfoil plunges and pitches. So we will be doing it. Let me go to the next slide. So we will be the outline of this you know, demonstration will be that we will be slightly looking at the aerodynamics of the flapping airfoil, and we will be looking at the different parameters of the flapping airfoil aerodynamics, and we will be setting off the case, and lastly we'll post process this in ParaView. So the problem is to we need to set up the case for the plunging. That is, plunging means the linear oscillation, or it can be a translation. So just to say, it's the heaving moment of the airfoil, and pitching is a rotating movement of the airfoil. So I think you know these two types of movement, and we can also, if time permits us, then we can also combine these two motions. We will see this, but if I can present it in this time frame, then I'll show it. So to another is to post process the result in ParaView and to explore some dynamics libraries in OpenCom. So what flapping motion? There are two equations. This is a simple sinusoidal equation. So in the plunging motion, we are finding the displacement by using y equals to sin omega t, which is a function of time, and theta is also a function of time. So as this both are the that these both are the sinusoidal motion equations. So where omega is angular velocity, and this is the same equation. So we can see in the figure that the plunging motion is the linear translation of the airfoil, whereas the pitching is the rotational angular displacement of the, where there is angular displacement of the airfoil. So linear displacement and angular displacement of the airfoil. So we can see that when the airfoil moves up and down, there is a change in angle of So when the airfoil is moving up and down, in the case of plunging airfoil, not for the pitching case, just for the plunging case, let me explain this. So when the airfoil moves up or down, so we can see that there is an effective angle of attack generated due to the velocity, due to the airfoil, that due to the wing and due to the free stream velocity, we have effective angle of attack, and we can see that the thrust is being generated. Some part of the lift is being converted into thrust due to the generation of angle of attack, and we also can note that this velocity of the wing will change with time, because if you do the derivative of the y equals to sin omega t, we also get 8 omega cos omega t, which is also a function of time. So as this velocity changes, the angle of attack will also change. But in both the cases, we can see that thrust is being generated in the forward direction, so there is generation of thrust. But we have to have a certain combination of the amplitude and the frequency of the airfoil, then only we can produce thrust, or it might also result in drag producing wakes. So this is the thrust due to lift, but there are also many other factors that will influence the movement of this airfoil, and that will influence the aerodynamic force in the airfoil, like the vortex setting, like the wake formation. So these are other things that will affect the forces or the aerodynamic forces in airfoil. So these are two different important numbers that should be considered while simulating or while understanding the flapping aerodynamics. So the first one is the reduced frequency. So reduced frequency, nothing but the ratio of the flapping velocity with the free stream velocity. So this factor determines that when the value of k is high, vortex remains in the airfoil for longer period of time, whereas when the reduced frequency is low, then the vortex is shed quickly. So this reduced frequency will also have to determine the steadiness or unsteadiness of the problem or the wing. So the other important factor or the important dimensionless number, so these both are dimensionless quantity. So is the strong number, so which is the product of k into a divided by c. And for flapping wings, you can use 2ks divided by pi c, where a is the wake width and h is the plunging amplitude. So for flapping wings, the wake width will be equal to the tip to tip distance, or the length swept out by the wing while it moves. So we can see the equation here, and we can see the strong number is a function of reduced frequency and amplitude. But we also need to study these parameters independently. So the strong number and reduced frequency should be studied independently while doing the flapping case, because if the product of k into h is 10, then k might be 2 and h might be 5, or k might be 5 and S might be 2. So in these two cases, the effect is different. So we must independently observe these two numbers while doing our simulations. So this is just for information. You can also check this detailedly, go to different research papers and see how this amplitude and how this frequency affect the aerodynamics of the flapping airfoil. So I think this is clear to some extent now. So this is the computational domain that we will be using. That so we will be using the k omega shear stress transport model, and the Reynolds number where we will be simulating is for 10 to the power 6, and we will be using morphing mesh. And what is different is that we will be we'll have to include the dynamic mesh dictionary in constant folder, which is different in than the other static mesh cases. So the only difference is dynamic mesh dict for the solid body motion solver, and for the displacement Laplacian solver, we need to include the point displacement file as well. So which we will see now. So let's run our terminal. So I'm running this in WSL in Windows. So I have used OP9 to alias the to source the OpenFOAM version 9. And let's go to our own directory where I've saved my files. So I have here moving airfoil, and here I have the cases for pitching, plunging using displacement Laplacian, and the flapping wing, and the so let's go to plunge. This is and let's see here. Now let's we have our this is for the plunging motion. So what are the files required? We will see it first. So let's first see the block mesh file, because we need to first generate mesh. So the block mesh file is located in, so we can see that the block mesh dictionary is located in system folder. And let's see. So this is our block mesh file. So we have imported the geometry of the airfoil as the tri-surface mesh. So we can directly use the OBJ file and then import it as tri-surface mesh, like we did in the SnappyX mesh that Ivan presented. So, and here we are using the searchable cylinder is for our simplicity. So the searchable cylinder we can, so that we can use the edge of the cylinder, the coordinates of the cylinder in generating our mesh. So here we use the project command for the mesh generation. So we have projected the coordinates that are required in the cylinder. So let me show the block mesh file. The blocks. So we can see that these are the blocks and the vertices that are being generated in the figure. So we have projected the coordinates of the cylinder from the coordinates to the cylinder or into the airfoil, which is required, and we will use these coordinates to later to generate edges, so that we do not have to use individual points in all these cylinders. So we can directly use the edge of the cylinder and the airfoil. So we have put the 0.3, the zero vortex is located in the z direction, as you can see by cursor. So this point vortex is being projected in the cylinder here, and at x equals 0.3. So this is the x equals 0.3. So to show that the plane that we are drawing this block mesh is xz plane, and y is the outwards plane that is coming out of the screen. So this x is in the horizontal direction and z is in the vertical direction. So we are at x equals 0.3. There are only two coordinates of the cylinder. That is either this coordinate or either the upper coordinate. So we need to project. If we project a point in this in the cylinder at this x equals 0.3, it will be projected either to the downward lower radius downward radius cylinder, or it will be projected to the upper point of the cylinder. So if we assign negative direction, that is here, we can see that in z we are projecting -5. So if we are using -5, then it will project the point in the lower part of the cylinder. And if we use +5, otherwise if we use plus direction, then it will project in the upper direction. But it is to note that this magnitude, that is 5, does not affect our meshing process. It can be either 10, 11, 12, because we only have at x equals 0.3, we only have two coordinates in the cylinder, that is this and this. And for the airfoil, and we are doing it for the x equals to y equals to minus 0.1 plane, and other is the y equals 0.1 plane. So that is the backwards and the forward plane, front and back plane. And we need to assign the blocks. So let me see, we have assigned, I will say the first block, I'll explain the first block. So it is 7, 4, 16, 19. Using this, we can see in the figure that 7, 4, 16, and 19 is one. And we have created the block using 7, 4, 16, 19 vertices and 0, 3, 15 together. So using this and this is, we have created one block. So that is the first block, and we have assigned the simple grading as well as age grading to these edges. So we have given the age grading to the edges, and we have graded we have given the simple grading to these directions. So you can go through these files, how are these blocks generated, and you can look at it later. So this is some complex block mesh. So you can first you need to have a basic idea of how to generate the mesh in block mesh before going to these files. Or you can also use open source GMS's software, which is also good for meshing the C-shaped the airfoil. So we are projecting the edges as well. So what is the benefit is that we do not have to include all the coordinates of the airfoil in our block mesh file, but we can project the edge directly in the airfoil so that we do not have main or vertices in our block mesh file. So this is one of the benefit of using the project function. Our boundary is the inlet. We have the top, and there is no top and bottom. There are only inlets. In the forward is the inlet, and the top and bottom are also given as inlet, and this is given as the outlet and the airfoil patch. So these are the boundary definitions. So you can check this out later. So how we have assigned the traces and the vertices. Okay, this after the block mesh dict is ready, we need to run the block mesh command. What control dict? Okay. So see that we have our mesh ready, and we can visualize in Terraform. So you can see our mesh is ready now. So we have created a structured mesh of our airfoil. So after the meshing process is done, let's now get into the boundary conditions. So to be able to see the boundary conditions are located in the ILWO original folder. So we can see that there are different files. That is the U velocity file, the pressure boundary condition to be assigned, and K, nut, and omega. So we can see that the K, nu, T, and omega comes from the K omega SST model, because we have used the turbulence model in this case. So if you want to see which model that we have used, then we can go to CD constant, and then so we can see that we have used the RAS model, that is the Reynolds average Navier-Stokes equation, which just means that we are representing the fluctuating terms in terms of the average mean flow. So we have used the Q omega SST model, and we have on the turbulence. So for cases in the flapping airfoil where there is the flow separation, so the K epsilon model is not good enough to locate the separation point. And in for cases like in adverse pressure gradient, we cannot use the K epsilon model. We cannot directly use the Q omega model, because the Q omega model is dependent on the free stream turbulence. So if there is a free stream turbulence, then that will affect the accuracy of the solution. So we have used the K omega SST model, which is the blend of epsilon and K omega model. So after that, let's go to our boundary conditions. So, as I've already mentioned in the previous presentation, that we need to assign the moving of velocity in case of dynamic mesh simulations in the U file. So, when the airfoil moves, then we need to assign this type of boundary condition. So, we have provided the internal field to be 1 meter per second, and at the inlet also we have used 1 meter. We have provided a velocity inlet of 1 meter per second, and we have used the in the outer we have used the Rowan boundary condition, that is the inlet outlet. So, when the recirculates, then the value of the inlet is assigned when the flow is recirculating at the outlet, and if it is not recirculating, or if it is traveling from inlet to outlet, then we will just use the zero. Then it just uses the zero gradient boundary condition. So, and we are as we are doing the 2D simulation, we are keeping the front and back plane as empty. Now let's do under pressure boundary condition. So we have given zero gradient at the airfoil, and fixed value at the outlet, and zero gradient at the inlet and type, and the front and back we have kept it as empty. Now there are also the boundary conditions for K, nu T, and omega, which is the K is turbulence kinetic energy, nu T is the turbulence viscosity, and omega is the specific turbulence dissipation rate. So you can also later see what is inside this. Well, let me see one. Let me show you then for the omega, that is the specific dissipation rate. We have used the internal field by using this formula, omega equals to K 0.5. So you can find this formula, and you can calculate your internal field. And we have used the omega wall function. So the wall functions are basically used when the y plus value is larger. So in order to simulate the cases with the adverse pressure gradient, we need y plus to be very small, but we cannot achieve that always, because of the computation limitation, and we cannot make the boundary layer very small. So in this case, we have used the omega wall function, because our y plus is greater than 30, that is from 30 to 200. We can use this wall function. So you can check when to use this wall function, and if in the later. And inlet also we have given the fixed value, outlet we have given inlet outlet boundary condition, and front and back is kept as empty. So you can check these other boundary conditions for the turbulence modeling, because we are not focusing much on this now. So you can later check which one you should use, which is better for you, depending upon Reynolds number, turbulence turbulence simulations. So now let's go to our dynamic mesh dig file. Okay. So in the constant, as I have said, that we have our dynamic mesh dictionary. So let's see what is inside the dynamic mesh dictionary. So as you can see that we have our dynamic mesh solver as an interpolating solid body. So before going to these, let me quickly show what solvers are available, and how can we use them. So let me. So when we go to the source folder, that SRC folder, then we can navigate to dynamic mesh. So in dynamic mesh, we have the motion solvers. So let's go to motion solvers. So in the motion solvers, let's navigate to displacement solvers. So in these, the solvers do not solve displacement Laplacian equation. These are just solving by transformation of the point. In order to solve Laplacian equation, to solve the Laplacian equation, we need to navigate to the active motion solver. So which I will show in a short while. So in the displacement solver, we have the solid body solvers. So if we go to solid body solver, now we can see that the interpolating body solid body motion solver. So we have used this solver in our dynamic mesh file, that the interpolating solid body. And if we go inside the interpolating solid body, we have the source codes available. Now if we check the source code, so if we see the source code, then we can see that it looks up for the input data required are the patches. So we have provided patches. That is it is and the other one that the input required is the COFG, as coefficient of gravity, and the inner distance and the outer distance. So we can look at these two uh, terminal and see that what are the inputs that are required in the interpolating solid body, and we have provided the input accordingly. So this is what I want to show. And if we want to see what are the motion functions that are available, then we can go to let me see. We can go to solid body motion functions. That is solid. You can see in my terminal motion functions. So what are the motion functions available? We can see this. So we can see here that there are different type of motion functions. These are the predefined motion function, that is the prescribed body motion. So here are linear motion, oscillating linear motion, rotating motion, solid motion functions. So what we have used in our case is that we have used the oscillating linear motion. So we can see that we have used the oscillating linear motion. So let's go inside. So there is also a source code .c file. So if we go into this, then we can see that inside this, we can see that what equation that does it solve is this. You can see that vector displacement equals to amplitude into sine omega t. So I had already shown you in the slides that what are the equation that we will be solving. So we can see that we will be solving amplitude into sine omega into t, and the inputs that that it looks up for is the amplitude and omega. So which we have provided here in this next terminal. We can see in the dynamic magnetic file. So we have provided here the amplitude and omega as well. So this is our dynamic magnetic file. Interpreting, we have used the inner distance and outer distance. So inner distance, so these values have to determine the scaling value factor to the mesh. So inside the distance of 0.01, that is if we draw a circle of 0.01 and draw a circle with radius 4, and in the radius of 0.01, there is actual mesh movement. There is no deformation. So in between this 0.01 to 4, there is mesh deformation, and outside this outer distance 4, there is no any mesh movement. So we can assign our distance, we can assign our domain with different values of mesh deformation by assigning this inner distance and outer distance. So this is the importance of this inner distance, outer distance, and the interpolating solid body motion solver. So after this, I want to show you. Okay, now let's check our. So these are transfer properties that we have used since we are simulating for RE equals to 6 case. 1 is 6, that is Reynolds number equals to 1 is 6. Then we have used the kinematic viscosity value accordingly. So we have used this value to make RE equals to 1 is 6. So I think you all know this, how to set up the transfer properties. So as RE equals to U into L divided by kinematic viscosity. So in this case, we have used kinematic viscosity as this value. So that's all. Now after dynamic mesh depth is very less, now we can now run our simulation. So before that, let's see our all-round file. What are the commands that So we are first copying the original file to the original 0.OD20 folder. That is the initial where the initial boundary condition will be stored, that is in 0 folder, and we will run the blockmesh command and decompose path, that is that decomposing the subdomains into different domains. So we are using 6 number of processors according to my system capability. So as Jungsur has already explained about how to decompose, what are the decomposition methods. I think I don't have to provide information on that more. So I've used the parallel decomposition in this. So I will be running the simulation parallelly. So after this, just to now we can type the all run command. Now you can see that our simulation is running. So I think I don't have much time to wait for the simulation. So let me go to other fold other cases as well. Okay, I think I saw in the Explorer. So I gave you the information. I showed the setup for the plunging motion. So what if there is a pitching motion? So if there is pitching motion, everything is same. Just we have to change some thing in the dynamic mesh dictionary. So let's go to our dynamic mesh dictionary. Okay, so we can see that we have also used the interpolating solid body solver in this case, but what we need is the origin. So this is the additional parameter that is not available in the plunging case, and we have to give the oscillating rotating motion coefficient. So when we see this motion function that when you see the source code of this motion function, then we can see that we need to also assign origin. So this origin is computed from the COF, that is coefficient of gravity point. So we have assigned a coefficient of gravity as 0.500. So what does this origin means is that we are going negative direction from 0.5 in to a magnitude of 0.25. So if this is taken at the center point, and the value is measured from this point, from the COFG, coefficient of gravity point. So what does origin means is that we are moving 0.25 in negative direction from the point 0.5 comma 0 comma 0. So this is our origin, and about which the about which the airfoil rotates. So this is our center point. So this is the only difference that can be seen in the pitching case. So other all things are same. So you also need to determine the amplitude. You can vary your amplitude omega, that is the angular velocity, and check what different results that you can get. So here we have used omega equals 6.28. I think this gives us the time period of 1 second. So at 1 second, it will move from its mean position. It will oscillate 360 degrees and come back to its original position. So this is this also helps to interpret our results. So this is the case for the dynamic mesh dictionary of the pitching effort. So for the let's go now for the flapping. That is flapping. These all are the flapping cases. So we will combine these two motions in our dynamic mesh dictionary. So we can see that there is also multi-motion available in the motion coefficient in the motion functions. So we can see that in the motion functions we have the multi-motion. So we can see a multi-motion in the terminal here. So we have used this multi-motion function to prepare the dynamic mesh dictionary file. So we have used the multi-motion function, and we have combined the linear oscillating rotating motion and the oscillating linear motion into this one single multi-motion file. So we can see here we have assigned pitching and plunging and given the same amplitude, the same omega that we had done for the pitching and the plunging cases. So here we can see, and we have to assign it to a path, the path that is moving. So there is the airfoil that is moving, and the coefficient of gravity. So these are the all these parameters and values are same that I had shown you in the previous case. Okay, now let's visualize our result. I think our simulation is done now. Okay, now let's open terminal here. So I'll be launching Paraform. So let's check out for the plunging case. So this is our initial condition at 0 time. So we are just at 1 meter per second at the internal field. So this is the case that is being shown. So let's first look how our mesh is deforming. So okay. So as we play, we can see that the mesh deformation is taking place. That is, the mesh is changing its shape and also moving, so which is the morphing mesh strategy. Okay, now let's check the velocity field. Now, yeah, we can see the vortices being formed and the circulation, the flow is circulating in the region. So if you want to clearly visualize this, so let's draw. So you can add filter using the control space and add the field to add the vector field. So yeah, the arrows are very large, and you need to keep the orientation area as velocity. Let's make it 2D first. So yeah, we can see that the for the velocity, okay, we have set this to velocity. It was before it was pressure. So we can see how the flow is bending and the flow is curling in these sections. So these vectors give us the description. This gives us the visualization that how flow is bending in these areas or is curling in these areas. If you need a better visualization, then we can just decrease this and okay. Now let's play our simulation. So here we can see that the vectors are changing the direction as the airfoil is moving. And there is also flow separation that is taking place in the leading edge. You can see here. As well in the trailing edge, the flow will the call and separate from the trailing edge with the vortices are formed. So this is for the velocity vector. So now we can also compute our vorticity. So in order to compute the vorticity, we need the gradient of the velocity. So this where we can have the options for computing vorticity. So we can just click apply. Now let's disable this, and now we can see that there is an option for vorticity available. Now let's customize this because there are some places that are very high values of vorticity, so which will not which will not visualize properly. Okay, now let's play this. So here we can see that the vortex and vorticity magnitude plot, and there are formation of vortex in the leading edge as well as in the trailing edge, where the vortex are being separated from the leading edge. So this is what I wanted to show. And one other thing that I also want to show is let's extract the wall filter. So if we press Control space, then we can access filter by searching the filters. So let me extract the airfoil. So we have our airfoil here. Let me slice this airfoil in the warm arm direction. But our So here we can see if I hide this plane. So here we can see that we have got a line of our wall, that is of our airfoil. Now when we plot the velocity in this airfoil, so let's go and plot where is the plot on sorted lines. What we see is we have the velocity in of our wall, that is in no slip condition it needs to assign zero velocity at the wall, but in this case we can see that the velocity is changing. That is the boundary condition. We call that the moving wall velocity boundary condition. So this is uh, what is really happening in the airfoil wall. So this is what I wanted to show you. Now we can also plot drag and lift in this in paraview. So let me plot drag and lift. So first we need the block to be extracted, which we have extracted. Now after we have extracted the block, we need to add a filter, which is generate surface normals. So what does it do is it generate the surface normals of the surface. So we need to compute shell normals and tick the box here. Now after we have generated surface normal, we need to access the calculator, and let's suppose this plot drag value. What we need to do is, since the pressure force in the acceleration gives drag, so we need to access. We need to multiply the normals and the acceleration with pressure. Now this will give us a drag. So we also need the drag coefficient, because that is what we are going to plot. So in order to plot the drag coefficient, we are plotting drags divided by the let me show my presentation. So this is the formula to plot the drag and lift. So half rho v square, since rho is 1 and half means 0.5, and v velocity is also 1 meter per second, and the area is, what is our area is the planform area of the airfoil. So since our height in the y direction is 0.2, so we need to multiply the chord length into 0.2. So in the block mesh file we have seen, we can see that let me show you the block mesh file. In the block mesh file, you can see that we have minus 0.1 to 0.1. So this means that our height in the in the y direction is 0.2 meters. So in order to find the area of the top surface area of the airfoil, that means we need to multiply the chord length times the height of the block mesh in the front and back plane. So what we do is we are dividing now by 0.5, which is half, and multiplying by 0.2. This way we can calculate our drag, and now we need to integrate this over our airfoil surface. So after integrating, I think we have got. Now if we plot this over time, then we will get our drag coefficients. So I have included the figure that I have plotted in paraview here. So we can see that the drag is in negative direction, which means that the thrust is being produced. That I had said that by certain combinations of the plunging amplitude and the plunging frequency, that is the reduced frequency, we can produce drag, or the wake can produce drag, or the wake might produce lift, might produce thrust. So in our case, we have got the thrust, and in the lift, you can see that the positive and negative direction of the lift, because I had already shown in upstroke and downstroke when the airfoil plunges, the lift is in positive direction, and when it is upstroke, then lift is in negative direction. So this is the cause for the positive and negative direction of the lift. And since the angle of attack is continuously changing, we have our continuous change of the CL and CD. So here we can, here I visualizing for the okay, we have our plot ready here. If we plot CD, so here we can see we have plotted our CD. Now another way to plot CD is by going to our first because we have also functions that are available, built-in functions or open form that are available to that are available for us to plot the first coefficient. So this is the for in the first coefficient file we need to assign these parameters, that is the patches, that is the row value, and the leaf value, leaf direction, drag direction, then the magnitude of the velocity, and area reference. So we have used the area reference 0.2, and this way we can also plot our first coefficient, and this will also give the same result that we have plotted in the paraview. So if you want to plot this in the Excel, then you can also plot this. So let me plot drag in Excel first. Now let me insert let me chart and select data. So let's name it CD, and let's plot from 0.01 to now let's also plot our CD from 0.01. So we can see that we have got the same plot as that we have plotted in paraview using the first coefficient. Let me show it in my slide. So this we have got the same plot as in paraview. So we can plot either of both of the either of these methods. So you can it's better to plot using the first coefficient data because these are calculated by the open source built-in functions. So we have seen the velocity contours, vortex setting phenomenon, vortex setting of the okay. In this way, you can plot the various parameters in paraview and post-process the results. So let me close my paraview now. Now I also have some simulation results of video animation of the for the flapping case. So you can see that the airfoil is plunging as well as pitching. So I have used the multi-motion function in this that I had shown you. So in order to use dynamic mesh in conform, we need dynamic mesh dictionary that is to be included in the constant folder. Now one thing that is left to show is the displacement Laplacian. So I had said that we can also use displacement Laplacian where this Laplacian equation is solved. So let's go into dynamic mesh dictionary and let's see that here we have used the motion solver as displacement Laplacian and diffusivity as the inverse distance and assigned to our moving path, that is the airfoil. So you can also use velocity Laplacian or displacement as straight depending upon your problem. And what we need to include is that we need to include the another necessary file, that is the point displacement file. So it is in this file where you give the motion function to the moving boundary. So in this case airfoil, we are giving oscillating displacement, we are giving the amplitude, we are giving omega. So in this way you can provide the motion, prescribed motion to the boundary. So if you have used velocity Laplacian, then in case of point displacement file, you must use the point motion u file. So this is the only difference that between the velocity Laplacian and the displacement Laplacian. If you are setting up a case with these two different motion solvers. So yes, I think we have come to the end of our session. So I think this is the end. So I would like to thank Professor Sundan Bose, Mr. John Pinto, for their invaluable guidance, and I'd like to thank the audience. And okay, so thank you. If you have any question, then
Yeah, thanks a lot, Manjil.